open circuit characteristics and short circuit characteristics to draw for an alternator for calculation of the regulation of the alternator. We need these two test data, that is open circuit characteristics data and short circuit characteristic data. Thereby we are finding out the data related to find the regulation of the alternator by different methods. Then how to conduct the open circuit test and the short circuit test on the alternator, just we'll discuss, and further we'll discuss how to find out the synchronous impedance from OCC and SCC. In this test, the open circuit test or open circuit characteristics name itself suggests that is the alternator is operating under no load condition. Then you are running the alternator at a rated speed. Then in steps you will go on changing the field current. For the different value of the field current, you are noting down the open circuit voltage. Then you are drawing a characteristics, that is the field current versus the open circuit voltage. That characteristics what you are getting is open circuit characteristics. The same thing is explained here. In this test, the machine is run by a prime mover at a synchronous speed. Generate voltage at the rated frequency while the armature terminals are open circuited. I'll show you in the figure in which the switch S should be open. Means you are running the machine under no load condition, keeping the frequency constant. That is, the speed of the machine as remains the constant. The reading of the open circuit line to line voltage VOC are taken for the various values of the field current, that is a rotor field current. Then the circuit setup for the open circuit, the characteristics is we have got a alternator, it is represented by 3 winding. Then we have got a field winding, it is represented by a winding, and I have shown here the field current. It is, you can vary for a different field current. You have to know about what is generated voltage. You have got a field winding, you have got an armature. The field in the case of the alternator is rotating with a synchronous speed, that is rotating with a synchronous speed. Then we have got a switch, then there is a voltmeter, then switch S, and there is another setup for conducting the short circuit test. That is, when this switch S is open, in that case machine is under no load condition and we are running the machine at a rated speed, and in steps you go on changing the value of the field current. For different value of the field current, the open circuit voltage, you are noting down and you are drawing the characteristics IF versus VOC, that gives the open circuit characteristics. So very simple, the experiment on the alternator. The next one is the short circuit characteristics. The name itself suggests that is, you are to conducting the test while shorting the terminals of the alternator. How we are going about this? Once again, the short circuit characteristics of the machine is obtained by means of short circuit test conducted as per the schematic circuit I will show you. In this test, the machine is run by a prime mover, once again at synchronous speed, with the rotor field kept unexcited to begin with. It is a very important point you have to remember here. That is, by conducting the short circuit test, then at the time of starting, the field of the rotor should be kept at minimum quotient, because if you have got a high value of the field current, in that case it generates the more voltage. When if it is short circuited and it is delivering the very high short circuit current, which is more than the rated current, so that you should not exceed the current more than the rated current under short circuit condition. Therefore, the extra care should be taken that at the time of starting, the excitation of the rotor should be the open. Then once it is runs with a rated speed, then gradually you have to increase your field current so that short circuit current should not exceed rated current. The short circuit current should not exceed rated current. Therefore, you have to be very careful of excitation of the rotor under short circuit condition. The field excitation is then gradually increased till the armature current equal to its rated value. Then you can note down the corresponding value of the field current in the rotor, that is the rotor field current. For different values of field current, what is should be the short circuit current you have to note down that short circuit current should not exceed the rated current. Below that you have to take 2 or 3 sets of reading, then you can draw the short circuit characteristics. The short circuit characteristics is a linear characteristics, then there is one point is also sufficient to draw the short circuit characteristics. That is setup is once again it is the remain same. It is consist of a winding, that is armature winding, it is a field winding. Then the field is rotating with a synchronous speed. Then the alternator having a switch, that is initially you start with the open switch, keeping this field current minimum or 0. Then you can close the switch so that in turn all the terminals are shorted here, all the terminals are shorted here. Then this ammeter reads the short circuit current in R phase, Y phase and P phase. You can take any one of the ammeter reading because the system is the balanced one. Therefore, for different value of the field current, you note down the what is the short circuit current. Then care should be taken that this current should not be exceed the rated current of the alternator. Okay. Of course, when it is short circuited, you can observe here the voltage is become a 0. That is how you are short circuiting, and for different value of the field current, you have to know the value of the short circuit current from the ammeter. Then, if you have got a data of one is from open circuit characteristics, wherein we have got a different value of the field current, we have got a open circuit voltage. For short circuit test, for a different value of the field current, we know the set of short circuit current. Therefore, two characteristics you have to draw on a single graph with the common base of the field current. Therefore, what I am doing here is, first on x-axis I am taking the base as a field current, which is common for both open circuit characteristics and short circuit characteristics. Then on one of the y-axis, what I am taking is the OC voltage. Preferably, you can convert that into the phase value. Even though in the data, in the numericals, if the values are given line to line values, better to have convert that into the phase value, then draw the characteristics. Therefore, I am on the y-axis, I am marked here as a OC voltage per phase. Then, from the open circuit characteristics, for a different value of the field current, you have got different values of open circuit voltage that you can draw. Therefore, we are getting the open circuit characteristics, that what I am calling is the OCC. Then, there is one more line I drawn, which is the tangent to the initial portion of the OCC. That is what we are calling is air gap line. It is called as the air gap line. That is the line which is the tangent to the linear portion of the OCC, or in other words, it is unsaturated region of the OCC. That line is called as the air gap line. Then I have got another the parameter I am taking on a y-axis, that is a short circuit current, that is ISC. For different value of the field current, I know the different values of short circuit current. Then you have to draw the characteristics. What you are getting is short circuit characteristics. Therefore, you are getting the two characteristics. One is the open circuit characteristics. The other one is the short circuit characteristics here. Then, from the open circuit characteristics and short circuit characteristics, what I have to do here is I have to find out the synchronous reactance of an alternator. Synchronous reactance of alternator. Then the question arises here is that where you have to take the point of the open circuit characteristics, because we know that the definition of the synchronous impedance ZS is open circuit voltage by the short circuit current. Therefore, you can see here there are two different regions in the OCC. One is called as a linear portion, that is called as unsaturated region of the OCC, that is a magnetic field, and the other one is the saturated portion. Suppose if you are choosing the point to find out the synchronous impedance, thereby synchronous reactance in the linear portion or unsaturated region, then the reactance what you are getting is called as unsaturated synchronous reactance. If you are choosing the point on the OCC in the linear graph of OCC, that is unsaturated portion, then what reactance we are getting is unsaturated reactance. Suppose if you are choosing the point in the saturated region, then the reactance what we are getting here is, it is called as adjusted reactance. It is called as adjusted reactance. First we will go for then how exactly you have to find out the unsaturated synchronous reactance. Then unsaturated reaction can be calculated from the OCC and SCC such that you have to choose the point on the air gap line. Air gap line means this is the air gap line or the linear portion of the OCC. It is one and the same. Means what I am doing here is I am choosing a point on a OCC in a such a way that it is on the air line or the linear portion of the OCC. Then for one particular field current, what should be the open circuit voltage? What should be the short circuit current? Means because impedance is defined as is open circuit voltage divided by short circuit current. Therefore, it is VOC and the corresponding value of ISC. Therefore, this VOC divided by ISC gives the synchronous impedance, that to unsaturated region. It is in the unsaturated region. Therefore, what I am getting here is ZS is equal to VOC divided by ISC for the same field current. Then, if you are interested in synchronous reactance, that is unsaturated synchronous reactance, then we have got a standard formula, that is the reactance is equal to under square root impedance square minus resistance square. Therefore, it is ZS square minus RA square. It is under square root. This is how we have to find out the unsaturated synchronous reactance of an alternator. The same points are repeated here. Just you can go through this. The OCC exhibits the saturation phenomena of the iron in the machine. At low value of IF, when the iron is in the unsaturated side, the OCC is almost a linear. That is what I am calling is this portion. The straight line part of the OCC, if extended, that is a straight line portion of the OCC is extended, that is become a air gap line. That is, it is called as an air gap line and would indicate the OCC if iron did not get saturated. If the iron is not saturated, then your graph will be a straight line. That is just like it is follow the air gap line. But if that is not the case in the case of the alternator, because there is a saturation in the magnetic circuit, thereby as the field current is goes on increasing and sooner or after there is a saturation, it is the magnetic material is reaching. Therefore, if you are taking the point of the unsaturated region of a OCC, then if you are finding out the impedance, that what we are calling is VOC by ISC, that particular the impedance is called as unsaturated impedance. Then reactance can be calculated from this ZS as ZS square minus RA square. Then VOC value corresponding to the air gap line could be used. That is, this air gap line should be used to calculate the synchronous impedance for unsaturated, finding out unsaturated synchronous reactance. Then how to calculate the adjusted synchronous reactance? Once again, the data required here is the open circuit characteristics and short circuit characteristics. That is the open circuit characteristics. Then the air gap line is not necessary actually here. Then we have got a short circuit characteristics. Then to find out the adjusted synchronous reactance, the point on the OCC you have to choose in such a way that the point corresponding to a rated voltage of the alternator, that you have to mark on the OCC. Usually that particular point is fall on the saturated portion of the alternator, because usually the alternator is operating operating in saturated region. Therefore, the common factor here is, that is, the point of how you have to take is the corresponding to the rated voltage of the alternator. You have to mark the point on the OCC. For that voltage, what is the field current, you have to note down. Corresponding to the same field current, what is the short circuit current, you have to find out. I will demonstrate here. That is, it is the rated voltage of the alternator. It is marked on the OCC. This is the corresponding value of the field current to generate VT rated under open circuit test. For the same field current, what should be your short circuit current? Means, while calculating excess adjusted, you have to mark the point on the OCC corresponding to the rated voltage of the alternator. Then you have to find out VT rated, that is nothing but the open circuit voltage, and ISC is the short circuit current for the same field current. Therefore, once again the procedure for finding out the ZS remains same. That is, ZS is equal to VOC by ISC. Thereby, once again IF is remains corresponding to VT rated. That is, IF you have to take in such a way that it has to generate the rated voltage under no load condition. Then similarly, the excess adjusted can be calculated ZS square minus RA square. Okay, that is why the same thing is written as synchronous machine is under operating condition, works in the somewhat saturated region of the magnetizing characteristics. The performance of the machine as calculated from the excesses. Whatever the calculation, the accurate results is yielding. Therefore, it is written here. Obviously, excess adjusted would yield the machine performance figures closer to those obtained under the actual operation condition. If you are using the unsaturated region reactance, in that case you are not getting the accurate result. However, in all the calculations you are using excess adjusted. Then one more parameter we are defining here, that is what we are calling is the short circuit ratio. So what do you mean by the short circuit ratio? Then I have got a open circuit characteristics as well as the short circuit characteristics. Then the short circuit characteristics is defined as, it is a ratio of the field current required to generate the rated voltage under open circuit condition to the field current required to circulate a rated current under short circuit condition. That is, it is the field current required to generate the rated voltage under open circuit condition, and it is the field current required to circulate the rated current under short circuit condition. That you can see here. For rated voltage, to generate the rated voltage under open circuit, the current required is what I am getting here is OF dash. Then to circulate the rated current, the field current required as OF dash. Therefore, OF dash divided by OF double dash, that gives the short circuit ratio. Okay, then we are studying in the higher semester what is the importance of the SCR. That is, the SCR is inversely proportional to synchronous reactance. How this SCR is play an important role in stability studies, that we are studying subsequently in our power system analysis.